Welcome back, children. Today we discuss quick revision of chapter Moving Charges and Magnetism. We begin with Ncert experiment. Ncert noticed that a straight current carrying wire has a magnetic field surrounding it in concentric circles. When current is shown by the thumb, then the other fingers curl in the direction of magnetic field surrounding the conductor. The strength of the magnetic field depending upon strength of the current. Direction of magnetic field also depends on direction of current. Also, the compass needle kept above the current carrying wire is found to be deflected in the direction of the new magnetic field shown by that current. Naturally, in the absence of current, the compass shows in north-south direction. But Ncert investigated when current flows from south to north, like this, over a compass needle, whose north pole seems to be here and south pole here, found to be deflected in the direction shown by the magnetic field. Right hand thumb rule can be used for finding the direction. Thumb will point the direction of current, fingers curl in magnetic field. Direction of magnetic field below the wire is into. So the north pole will deflect towards west. So when current flows from south to north, over the needle, north pole of the needle deflect towards west, so that you can easily remember this now. So this is the experiment, popular experiment done by Ncert. After that, many experiments were conducted, and the source of magnetic field was believed to be current. Current is the source of magnetic field. In hydrogen atom, electron revolving around the nucleus so fast, so it produces a current, and that current produces magnetic field. So streaming electrons also can produce magnetic field. That means moving charges can create magnetic field. From that it was concluded moving charges as magnetic field. Moving charges and magnetism. That's the name of the chapter itself. Okay, again, the current carrying wire is in the form of a closed loop. That may be a current loop. Again, investigations went on and found current loop is a magnetic dipole. A magnetic dipole has north pole and south pole. In magnetism, monopoles are never existing. Current loop is a dipole, it has north pole as well as south pole. The phase from which you watch is current clockwise, then south. Phase from which you watch the current seems to be anti-clockwise, then that phase is north. Anti-clockwise north and clockwise south. All this we have learned and revised very well. And this is about Ncert experiment. The direction of deflection of that north pole depends on whether it is placed below or above. Let us practice that for once. Based on a previous question. If you have two conducting current carrying wire carries currents in this direction I1 and I2. Let us notify 4 quadrants here. In first quadrant, the direction of magnetic field due to the current I1, is, using right hand thumb rule, you can see this. Thumb will show the direction of I1. So fingers curl outward above and inward below. So outward above and inward below. Now due to the current I2, To the right of that current I2, field is inward. To the left, field is outward. So here field inward, then here outward. And it can be seen that in first quadrant and third quadrant, the fields are opposite in direction, so the chance of minimum field is more. So minimum field is found to be in first and third, and maximum field found to be in second and fourth. And the chance of a null point means point where resultant field is 0 is possible in first and third quadrant, because field can be equal and opposite in certain points. Definitely field at the joining point will be 0. Current carrying wire, field along the axial point is 0. As this point, both the current carrying meet. Okay, not short circuiting because insulated. So field at that point is 0. Like that, there may be large number of points along this straight line where resultant field is 0. And that point join collection of null points give rise to a straight line. And that straight line will bisect that first and third quadrants if I1 is equal to I2. Hope that it is clear. Now, next we have to revise is the topic. What is the effect of a charge in magnetic field? For which we have to learn magnetic Lorentz force. Magnetic Lorentz force FB is equal to Q into V cross B. FB is the magnetic Lorentz force, that is equal to Q into V cross B. Cross product rule is used for finding the direction of magnetic Lorentz force, and that is right hand screw rule or Fleming's left hand rule, whatever. Popular one is right hand screw rule. You turn a right handed screw from velocity vector to magnetic field vector, first vector to second vector, then the direction in which that right handed screw advances will be the direction given by the magnetic force. So magnetic force is depending on magnitude of the charge, velocity of the charge, magnetic field, which is the external magnetic field in which charge is moving. If the charge is at rest, no magnetic force. Then one more factor over which force depending is that angle between velocity and magnetic field, which can be given by FV is equal to QVB sine theta. Is the magnitude of the force, and if theta is equal to 90, that when V perpendicular to B, force is found to be maximum. If P is parallel to B, force is found to be 0. That means if the charge is moving parallel to the magnetic field, force is 0. Charge is moving perpendicular to the field, force is maximum. Now let us learn what is the maximum magnetic force. Maximum magnetic force is equal to QVB. From this, unit of magnetic field can be Tesla. Tesla can be written as 1 Newton per ampere meter. So its dimension would be m t raised to minus 2 a raised to minus 2. Magnetic field is a vector. Its correct name is magnetic flux density. Flux density. Flux density means Weber per meter square. Weber is magnetic flux. So Weber per meter square is also another expression of 1 Tesla. Tesla is the SI, Gauss is the CGS. SI units are often used. So FB, F is equal to QVB, which is maximum Lorentz magnetic force. Magnetic force is a centripetal force. It cannot do any work. So it cannot make any change in kinetic energy. Work energy theorem says that work done is equal to change in kinetic energy by net force. Here, magnetic force is a centripetal force, that's why it does not do any work. So change in kinetic energy of the charge after coming out of the magnetic field will be 0. So magnetic field cannot make any change in the speed. It cannot make any change in kinetic energy. It can only make changes in directions. That is why magnetic forces magnetic force is always perpendicular to velocity. Magnetic force is always perpendicular to magnetic field. Acceleration of the charge is always perpendicular to, as force perpendicular to velocity, acceleration is also perpendicular to velocity. That is why F dot V should be 0. F dot V should be 0. A dot V should be 0. Among this one was tested in 2022 question paper. A dot V equal to 0 was tested in a numerical question. Okay, so that's very important. Magnetic force is always perpendicular to the component vectors. Magnetic force is a centripetal force. Okay, when a charge is entering at right angles to magnetic field, charge moves in a circle. The radius of that circular path is r. If the mass of the charge is m, the charge is entering along this direction. Let that charge be entering with velocity v. Let the inward magnetic field be. You can find out the direction of the force on it at the instant when it enters the magnetic field. Using right hand rule, the direction of entrance is direction of velocity. Direction of magnetic field is inward. Then velocity rightward, magnetic field inward, then thumb upward. So the magnetic Lorentz force acting on this positive charge is upward. If it was a negative charge, it would have been downward. Now the velocity changes due to that upward force. Velocity is along right, force is along up. So force and velocity at right angles. At every moment, force is found to be perpendicular to velocity. Goes in a circle of radius. R is equal to mv divided by qb. Time period, time for once to circulate, 2 pi m divided by qb. Frequency, qb divided by 2 pi m. Then momentum, P is equal to qbr. Angular frequency, qb divided by m. qb by m is angular velocity, v by r. Now kinetic energy, q square, b square, r square divided by 2m. All these equations are very important. Okay. So charge is entering perpendicular to magnetic field. It does not make any change in kinetic energy. It does not make any change in the speed. What is the acceleration of that charge? Acceleration is equal to maximum force divided by mass. Direction of acceleration is always directed towards center of that circle because it is the centripetal acceleration. So qvb by m is that acceleration. That is nothing but v square by r. One v gets cancelled. From this we can get r is equal to mv divided by qb. Say a equal to qvb by m. This formula is very important. Okay. Charge is moving with constant speed, but direction changes continuously. That's why it has an acceleration, which is qvb by m. If the charge is entering obliquely at the same time, charge is entering obliquely. Let this be the direction of magnetic field. Charge is entering along this line. Charge is entering along this line, and 2, that is a positive charge. Velocity is along this line, that is making an angle theta with the external magnetic field. This time the charge will move in a helical path. The charge moves in a helical path. This distance, which is the distance traveled by the charge along the field for once when it circulates, is called pitch of helix. Pitch of helix is given by the horizontal velocity, which is v cos theta. V cos theta is the velocity component of the charge along the field into time for once to circulate. That is Tv cos theta. That implies T is 2 pi m by qb. Previous page we have written into v cos theta. So 2 pi m v cos theta by qb is the formula for pitch of the helical path. Here, which depends on speed. If speed is a entrance speed is a constant, further there won't be any change in speed. Angle theta is the angle at which it enters, that's a constant. The only thing that may vary is the field strength. If field strength is kept a constant, pitch of helix is a constant. Okay, so pitch of helix is equal to 2 pi m v cos theta divided by qb. Okay. What's the formula for velocity? Velocity, momentum is equal to qbr. Velocity is equal to qbr divided by m. This formula is also important for finding the velocity. Now, the charge circulate by using the normal component of the velocity. V sin theta will be used for finding out the direction of velocity component perpendicular to the direction of magnetic field. V sin theta, that will decide the radius. So radius of that charge m v divided by qb. It was before we have learned r equal to mv by qb, but this time it would be m v sin theta by qb. So it would move with a reduced radius if it enters obliquely. But if theta equal to 90, it defines maximum radius. When theta reduces, radius reduces. When theta becomes 0, no radius, that means it is going undeflected, no force. So mv sin theta by qb is very important formula. When charge is entering normally, period is 2 pi m by qb. When charge is entering obliquely also, time period is 2 pi m by qb, no change. So time period does not change when it enters normally or obliquely. That's very important, students, note it. But charge when enters normally, radius is maximum. Charge when enters obliquely, radius is less. So radius is maximum or minimum. That depends on whether how it enters. Okay, so this pitch of helix, that formula is important. When a charge is projected perpendicular to both electric and magnetic field, what happens? These all are the exercises for the concerned topic. Suppose electric field is directed along y-axis, magnetic field is directed along z-axis, a charge is projected along x-axis. The charge is now projected along x-axis. Charge q is projected along x-axis. Where electric field is along y-axis and magnetic field is along z-axis, charge is projected along x-axis. What happens to that charge? That charge is affected by two forces, QE and QVB. As velocity perpendicular to magnetic field, magnetic force is maximum. You can also use Fleming's left-hand rule. In cases where you need to find direction of magnetic Lorentz force, four-finger magnetic field, when you hold your left hand, four-finger magnetic field which is outward, middle finger velocity, that is rightward, thumb force, that is downward. So the direction of magnetic Lorentz force is downward. At the same time, direction of electric force is upward. So electric force QE upward and QVB downward. A case may arise where QE equal to QVB, where Q gets cancelled, where you get V as E by B. So irrespective of the magnitude of the charge, irrespective of the charge to mass ratio of charges, those charges having the ratio E by B as its velocity will go undeflected in each of these fields. So when a charge is moving perpendicular to crossed electric and magnetic fields with the suitable speed, which is measured as the ratio of electric field and magnetic field, will go undeviated. This principle is called velocity selector and was used for the first time by whom? J.J. Thomson, while determining charge to mass ratio. So when you have a collection of charges having different charges, different charge to mass ratios, all projected perpendicular to crossed electric and magnetic fields, the charges which have speeds E by B will be rendered undeviated, perpendicular to both of the fields. This concept is very important. Okay. So in the presence of electric field and magnetic field simultaneously, there is a chance to have net force 0. There is a chance to have acceleration 0. If only electric field is present, definitely the charge is going to be accelerated. But if both electric and magnetic fields are there, there is a chance that the charge remains unaccelerated. Charge remains undeviated. Charge is not experienced by any force, provided electric field and magnetic field are to be perpendicular. Charge should be having a velocity, initial velocity perpendicular to both the fields. Then the ratio of electric and magnetic fields should be the speed of the charge, right? These are the very important topics of that chapter, very important topics of the chapter regarding Lorentz force and motion of charge in magnetic field as well as combined electric and magnetic field as given by NCERT. The next important thing is that what is the Lorentz magnetic force on a current carrying wire? Lorentz magnetic force on a charge moving with velocity v is F is equal to Q into V cross B. At the same time, if you have a current carrying wire, that current carrying wire carries a current I. It's a straight tube placed in external magnetic field B. Then hold your Fleming's left hand rule, you apply left hand rule here, forefinger magnetic field inward, middle finger current, then thumb force. So direction of magnetic Lorentz force, which is F is equal to B I L, where L is the length of it. So the expression for magnetic Lorentz force acting on a current carrying wire is to be studied, and there is a solved exercise. Let us practice that. If M is the mass of this conducting wire, mg is the weight is acting downward, that BIL is acting upward. So mg is equal to BIL. So you can solve any one of these parameters, keeping that current carrying wire stationary in midair without falling. So that current carrying wire can be made suspended in midair provided weight is equal to BIL, mg equal to BIL. Hope that you are clear. Next topic is Biot-Savart law. We have to revise Biot-Savart law. Biot-Savart law. The basic law can be compared with the Coulomb's law of electrostatics, which states that when you have a small current element may be ideal. Current element is a vector source. Draw the tangent to the center of the current element. Center of the current element is C. Draw the tangent. And this current carrying wire carries the current I. I is the current element is ideal. And you have a point P. Draw position vector from center C to that point P. Position vector is R. That position vector makes an angle theta with the current element vector. Okay, in vacuum. Permeability of vacuum is mu 0. Mu 0 value 4 pi into 10 to the power minus 7. Unit of mu 0 is Tesla meter per ampere or Newton per ampere square. Dimension of permeability, last time Neet question it was asked. Permeability of dimension Newton per ampere square, which is ml t raised to minus 2 a raised to minus 2. 4 pi into 10 raised to minus 7 Tesla meter per ampere or Henry per meter. So position vector R makes an angle theta with the proposed direction of the current. That's the current element at the point C. Okay. Now the magnitude of the small magnetic field dB due to that small current element ideal. Ideal is the current element, dB is the field due to that current element alone at the point P is given by magnetic constant, which is popular mu 0 by 4 pi I. I is that current I into dl. Okay, I'll write the numerical version. I dl sin theta divided by r square. So this field has a sign dependence, angle dependence, trigonometry is there, but in electrostatics for a point charge, for finding field, there is no such sine or cosine function. but magnetic field is of sine function theta 90, field has maximum strength. That draw a line perpendicular to pass C, then at any point the chance of getting a maximum field is more. Mu 0 by 4 pi is the magnetic constant. Okay, and its vector equation can be written as dB is equal to mu 0 by 4 pi I into dl cross r cap divided by r square. And it also says that if theta equal to 0, theta equal to 0 means that may be a point here. Theta equal to 180, that may be a point here. Theta 0 or 180, wherever magnetic field would be 0. So extend the current element. At any point on the current element, the field due to that current element happens to be 0. It is not certain that field due to other current elements in a given situation is 0 at that point. For example, at this point, field due to that current element is 0, but field due to any other current element need not be 0. So that is not the resultant field. We have to find the resultant field by using integration. That's the drawback of this. Okay, that's Biot-Savart law. Now, Biot-Savart law can be used for finding the direction of magnetic field and magnitude of magnetic field of a circular current carrying coil. You have a circular current carrying coil whose axis can be shown like this. Axis of the current carrying coil. Radius of the coil. Radius of the coil is R. And this is along Y axis. This is along Y axis. And this is along Z axis. And this is along X axis. And this is the current I. Current is flowing from Y to Z. The circular coil is kept along YZ plane. O is the center. Find a point P distant X from the center along the axis. Draw a line from the periphery of the circle to point P. That line also happens to be in same plane as that of X. Okay. Now, the magnetic field at P is measured as mu 0 N I R square divided by 2 into R square plus X square all raised to 3 by 2. Where N is the number of turns, I is the current of the loop, R is the radius of the loop, X is the distance measured from center to the point P. So students, BP is the field at the point P. Mu 0 Ni R square by 2 into R square plus X square all raised to 3 by 2. Don't forget this picture and also this equation. Very, very, very important. Okay. What about at X equal to 0? Field at center is given by mu 0 Ni divided by 2R where R is its radius. Okay. Another thing. Field at the center is mu 0 Ni by 2R. As you move away from the center towards infinity, what happens to the field strength? Don't forget that field strength first increases, becomes maximum, then decreases. All that might have learned in electrostatics. In electrostatics, we have already learned we have a charged wire. You may have some confusions there. Listen, you may have a charged wire whose electric field at the center is 0 and you move along the axis up to infinity, field strength increases, becomes maximum, then decreases. And it becomes maximum at X is equal to R by root 2. But here it is not like that. The field at the center is maximum. As you move away from the center, field decreases. Okay, field decreases continuously on either side. So field decreases continuously on either side. Field at the center is maximum, but in electrostatics, in similar situation, field at center is 0 and you move away along the axis, field first increases, becomes maximum at X equal to R by root 2, then decreases. Okay. So field at center of a circular coil is mu 0 Ni by 2R. What are the factors over which it depends? That's also important. Now you can reduce a shortcut between field and B0. B is equal to, at a distance x, is equal to B0 divided by 1 plus x square by r square all raised to 3 by 2. You can find out B at a distance x in terms of B0. So Bx is equal to B0 by 1 plus x square by r square all raised to 3 by 2. These type of questions are very important. If Bx equal to B0 by 8, if Bx equal to B0 by 8, you can see that 1 plus x square by r square all raised to 3 by 2 equal to what? 8. Okay. That is 1 plus x square by r square equal to 8 raised to 2 by 3. 8 raised to 2 by 3 is 64 raised to 1 by 3. That is 4. That is 1 plus x square by r square equal to 4. That is x square by r square equal to 3 and x is equal to root 3r. So this result is also important. What is the ratio x by r equal to root 3? This type of questions also may be asked. This is an application of Biot-Savart law. So field along the axis at a distance x from the center is measured as B0. B0 means field at center divided by 1 plus x square by r square all raised to 3 by 2, and by heart this result x equal to root 3r, field becomes 1/8 of the field at the center. So field reduces continuously as you move from center to infinity. Field at center is maximum. Now field due to an arc carrying current I. The arc is of radius r. Radius of that arc is r. The angle subtended by that arc at the center of this arc is theta. Now field is equal to mu 0 I theta divided by 4 pi r. This can help you in many situations. For a case where theta is equal to pi by 2, theta equal to pi by 2, theta should be in radian. If it is given in degree, you convert. Don't forget to convert into radian. If theta is 90, substitute theta pi by 2. If mu 0 I pi by 2, it becomes pi cancels, mu 0 I by 8r. That becomes a quarter circle. Total field due to circle is mu 0 I by 2r. Quarter circle is mu 0 I by 2r by 4. That is mu 0 I by 8r. That's very important. Okay. So field due to an arc of current carrying current I, mu 0 I theta divided by 4 pi r, it's going to be very important. Okay. Now the next topic what we have to discuss is field due to a straight, very straight current carrying wire of finite length. You have a current carrying, straight current carrying wire of finite length carrying current I. You notice a point at distance r from that current at the point P, and you have the mentioned angles theta 1 as well as theta 2. Then what is the field at the point P? Mu 0 I divided by 4 pi r into sine theta 1 plus sine theta 2. This also will help you. It is not mentioned in our textbook. In CRT it's not there, but may help you. So this can be deduced from Biot-Savart law, but that work is not in our textbook. That's why that is not indicated there. Okay. Next topic is Ampere's law. Ampere's law states that line integral of magnetic field around any closed path is equal to mu 0 times the current enclosed. Line integral of magnetic field around any closed path is equal to mu 0 times the current enclosed. What do you mean by this current enclosed? Current enclosed is the current penetrating through a closed loop surrounding that source of current. For example, if you choose an infinitely long current carrying wire, choose an infinitely long current carrying wire like this, which carries a current I. You have to find a magnetic field at the point P, distant R from the current, you construct a closed imaginary loop, passing through the point P, symmetric about the current. Now you take the line integral of magnetic field around that closed loop, which is given by B into 2 pi R, which is equal to mu 0 times the current penetrating this boundary, penetrating within this boundary, which is only I. You can only see that current only is passing through that closed loop. That is why B is equal to mu 0 I by 2 pi R. This result is also important. And also, field along the axis is 0. Field along the axis is 0. And away from the axis only you can use this formula to find. So that is Ampere's law. So this is one of the important applications of Ampere's law. Field due to infinite current carrying wires, mu 0 I by 2 pi R. Field due to finite current carrying wire, mu 0 I by 4 pi R into sin theta 1 plus sin theta 2. That two results are important. Next one, the second application is a thick long wire. You consider a thick long wire, and is a thick long wire whose axis is mentioned here, axis. So imagine a point P. You have to find the magnitude of magnetic field at P. P is at distance R. Imagine an Amperian loop. Amperian loop has radius R. So line integral of magnetic field is B into 2 pi R. Line integral of magnetic field along that boundary. That is equal to mu 0 times current enclosed. Current enclosed is current per unit area. Current per unit area is J, current density. Current per unit area J can be written as total current divided by total area, where capital R is the total radius, small r is the radius of the concerned loop. Small r is less than capital R mentioned here. So I by pi R square is the current density. So mu 0 times, what is the current enclosed? That means current penetrating through this concerned small area. That is current per unit area into available area. That is pi R square. One R gets cancelled, pi cancels, you get B. Mu 0 J by 2 into R. That is B varies linearly with distance if that point lies inside a thick long current carrying wire. Thick long wire carries current throughout its area. Everywhere it flows. But only a fraction, little bit, small fraction is only passing through the small tube of small cross section where it is at a distance small r. That boundary is at a distance small r. So that field is proportional to r. Also important, if small r is equal to 0, field is also 0, which tallies with the result produced by Biot-Savart law. Field along the axis is 0. So field due to a thick long wire inside, that is R less than R, inside, you can use this formula. Also you can substitute J, substitute for J and try to get another one. And for any other point outside you imagine an Amperian loop here, you can find out the field mu 0 I by 2 pi R. As earlier, a thin long wire, say we give same magnetic field outside. For exterior points, mu 0 I by 2 pi R, interior points, mu 0 J by 2 into R. And if you plot a graph between magnetic field along y-axis, it's a solved exercise in NCERT. You get a graph like this. So within BR graph, inside R less than R, be proportional to R. Outside it is going to be a rectangular hyperbola. Outside where R greater than R, hyperbola, R less than R, straight line. And field is maximum at the surface. Surface field is maximum. Third application is a solenoid. Solenoid consists of insulated copper coil wound in the form of a helix hook length is much larger than its radius. Solenoid can give strong magnetic field inside. Solenoid has negligible field outside when comparing with inside, so we say that there is no field outside. A solenoid is wound over a soft iron core. Soft iron is of high permeability. That's why soft iron increases the field inside, flux density inside. This is the axis. Turns per unit length of the solenoid is N, small n. Capital N is the total number of turns and small l is the entire length of the coil. Capital N is the total number of turns, small n is the number of turns per unit length. And if I is the current flowing like this, I is the current flowing like this, I. Direction of magnetic field. So hold your right hand fingers, don't forget, not left hand, right hand. Then thumb will point the direction of magnetic field, that's towards right. The field at the center of an ideal solenoid or a very long solenoid, exactly at the middle, B at center is equal to mu 0 N I. It's very popular formula. And if a soft iron core is inserted whose relative permeability mu r is equal to 100, then field becomes 100 times. Okay. So when a soft iron is inserted, soft iron has high permeability. Soft iron is a ferromagnetic material. This core has a property to increase the flux density inside the solenoid. So the field strength highly depending on number of turns per unit length, current, also medium or the core of the solenoid. Introducing a core, soft iron core, the field strength increases and becomes μr times. It's very important, this formula small n equal to capital N by L is also important. Then field at ends will be half this field. Field at ends is equal to half this field. Field at center is mu 0 Ni, field at ends is half the field. Mu 0 Ni by 2 is the field at ends. So that's solenoid. Okay, so insulated copper coil wound in the form of a helix. Field inside a long solenoid near center field is highly confined and field lines are parallel to one another. Listen, statement type questions may come. Long solenoid near center, field lines are parallel and crowded and highly confined. But on reaching to the ends, the field little bit it becomes curved and field is not completely confined and field becomes less curved also. Field lines, magnetic field lines are continuous closed lines. You can see that here direction of magnetic field is towards right along the axis. So direction of magnetic dipole moment of this solenoid is also along the field along the axis. So this is the direction of the magnetic field inside. Now it makes closed loops like this. So externally the same number of field lines make closed loop. But students, do you know why the field outside is 0? Field outside is never 0, but flux density is 0. That's the thing. Same number of field lines are there as there are inside. But flux density outside becomes what? Outside flux density becomes 0. Why? Because there is relatively number of field lines outside is less. Inside field lines are very much pressurized, high density, large density field lines are there inside. So this concept is important. Now the fourth application is going to be a toroid. Toroid is an endless solenoid. Toroid is an endless solenoid. Toroid is an endless solenoid. Same formula can be used for toroid also. Solenoid, but endless. Coil wound like this, endless, like this. You can see that current enters and leaves. The field lines are completely confined inside this toroidal coil. So field inside is circumferential. So the direction of current I am showing like this. Like this current is flowing through these turns, I am showing. Then what happens to the field? You can hold your right hand like this. So field inside completely confined and almost circular. Field lines circular and completely confined. But field well inside the toroidal coil is zero. Field inside is zero. Field outside also zero, because inside no current enclosed. Outside also no net current enclosed. So field, there is only circumferential field. The circumferential field is given by B0 is equal to mu 0 Ni. Same formula. But here the difference is that small n is equal to n divided by L. Here L is this length. L is this length. N by L is this length, but this time it is bent into a circle, into the shape of a donut. Then this length L is equal to 2 pi r, where r is the average radius. If r1 is the inner radius, r2 is the outer radius, r1 by r2 by 2 will you get small r. So small n is equal to n by 2 pi r, where small r is equal to R1 plus R2 divided by 2. Okay. So toroid field well inside R less than R1 field 0, R greater than R2 also field 0, but field is not 0 between R1 and R2, and that field is this one. Small n can be n by 2 pi r. Don't forget R how to calculate, R1 plus R2 by 2 in problems. Okay, so applications of Ampere's law also over. Now, we try to practice all this together. Two infinitely long current carrying wires. Two infinitely long current carrying wires kept side by side. Two infinitely long current carrying wires kept side by side. One is carrying current I1, other is carrying current I2. These two currents are in same direction, separated by distance d. Now, every unit length of each of these wires are under a force. We know like charges repel, but like currents in same direction. Like charges repel, like currents attract. So these two would attract. How? These two would attract. That means I1 is attracted by I2. And I2 is attracted by I1. So these two would attract one another with a force per unit length of mu 0 I1 I2 divided by 2 pi d. This is a very popular definition of 1 ampere. Basically 1 ampere current is defined using this only. I1 is equal to I2 is equal to 1 ampere and distance d is equal to 1 meter, then force per unit length is calculated. You can calculate 1 mu 0 by 2 pi is 2 into 10 power minus 7 Newton per meter. So define 1 ampere. 1 ampere current is that current which when flows through two infinitely long parallel straight current carrying wires separated by a distance of 1 meter experiences a force of 2 into 10 power 7 Newton per every meter per meter. So that's the definition of 1 ampere. So like currents attract, but like charges repel. Like there is a saying, like charges repel, and like currents attract. Similarly, unlike charges attract, unlike currents repel. So unlike currents repel, like currents attract. This is due to the fact that when you have a spring, you try to pass current through that spring. Three-dimensionally, it looks like this almost. Now what happens to the length of the spring on passage of current? On passage of DC, two neighboring coils are carrying currents in same direction. So like currents would attract. That's why the spring would contract. As a result of passage of current, the length of spring decreases. It's an old Kim question. It's very important. Okay, the next application is that torque experienced by a current loop in external magnetic field. Torque experienced by a current loop in external magnetic field. We have an external magnetic field. Here this I am going to show, which is the pole pieces of a magnet. Pole pieces of magnets, and we have a suspended rectangular coil. Suspended rectangular coil. The rectangular coil which is suspended about this axis. Okay. Now you pass a current through this coil. Current I. Now this is a current carrying closed loop. Current loop placed in external magnetic field. Current loop is a magnetic dipole. Current loop is acted upon by no net force in uniform magnetic field, but can experience a net torque. The torque given by torque tau is equal to M cross B. It's a working principle of a galvanometer. So torque tau is equal to MB sin theta, where M, moment of the current loop, is defined as NIA, number of turns into current into area. Moment has unit joule per Tesla, don't forget. Joule per Tesla, magnetic dipole moment has unit joule per Tesla or ampere meter square. Magnetic dipole moment is a vector. Direction can be given by right hand rule. For example, here current is flowing in this sense, anti-clockwise. Current is flowing in anti-clockwise sense, then what's the direction of moment? Outward, positive z axis. So torque is equal to M cross B. Turn right-handed screw from moment outward, field rightward. So moment outward, field rightward, torque is along the axis upward. So this is the direction of that torque vector. Torque is perpendicular to both moment and field. Torque is maximum when theta is 90, not torque when theta is equal to 0. Okay. In a situation in the case of a galvanometer, for example, a suspension type moving coil galvanometer, some adjustments are made for which that theta is always 90, for which torque is always maximum. And that maximum torque MB is equal to a proportionality constant into deflection produced by the coil present in the external magnetic field. B is the external magnetic field directed from north to south. So MB equal to C5, that is NIAB, NIAB or ABI, both can be used. C5. This is the principle of a moving coil galvanometer. Let me write it once again in the next page. NIAB is equal to C5. So I directly proportional to phi. C is a constant called couple per unit twist. C is a constant. The equation for C is pi. G R raised to 4 by 2L, where L is the length of the wire, R is the radius of the suspension wire, G is the shear modulus of the wire. Suspension wire is made of phosphor bronze. Phosphor bronze material is a special type costly alloy, which is the alloy of phosphorus and bronze. It is used because it has strength, strong, it's a good conductor. For getting a sensitive galvanometer, that is phi divided by I. Let me write at first phi by I. Phi divided by I. Phi by I is equal to NAB divided by C. Phi by I equal to NAB by C. This phi by I is called deflection per unit current. When you pass unit current, what is the deflection produced? That is called current sensitivity. So this will describe you the current sensitivity. For getting more current sensitive, a good galvanometer should be more current sensitive. That means a little current when flowing should show large deflections, for which NAB by C should be larger. N must be larger, area must be larger, field strength should be larger, but C should be lesser. For keeping C less, shear modulus should be less. For getting shear modulus less, also radius should be less. Okay, it should not break when you make it into a small wire. So it should be highly ductile. Phosphor bronze wire is highly ductile. It has low shear modulus, but it has large Young's modulus. All these properties are there. Good conductor, all that. That's why phosphor bonds wire is used as a suspension wire. And formula for current sensitivity is NAB by C. Don't forget this one. Okay. Now, a good galvanometer should be voltage sensitive also. For which Ohm's law I equal to V by R. So that you may write NAB divided by RC. Current sensitivity proportional to number of turns. Deflection per current proportional to number of turns raised to 1. But deflection per voltage proportional to number of turns raised to 0. Do you know why? Because N by R is a constant. On increasing the number of turns, automatically the resistance also would increase. N doubled, R doubled. So N by R is a constant. So deflection per unit voltage, that means voltage sensitivity independent of number of turns. Current sensitivity depends on number of turns. Current sensitivity proportional to number of turns. Voltage sensitivity independent of number of turns. Hope that it is clear. So current sensitivity and voltage sensitivity. What is the principle of a moving coil galvanometer? Current proportional to deflection, I proportional to phi. Galvanometer is a device used for detecting small currents. Okay. Now, conversion of a galvanometer into ammeter. How to convert a galvanometer into a measuring device like ammeter? Ammeter is a measuring device. It measures current and it should pass maximum current. So its resistance should be reduced as such, so that all the current passes through that. Okay, galvanometer is to be converted to ammeter by connecting a very small resistance in parallel with it, and that is called a shunt. Very important topic. If I is the total current entering, Ig is the current through galvanometer part, Is is the current through shunt part, we know I is equal to Ig plus Is. This relation is first of all important. Next one, voltage across galvanometer equal to voltage across shunt. That's why Ig can be written as how? Ig equal to, see how I am writing. Ig equal to the total current I into S divided by G plus S. Similarly, Is is equal to total current I into G divided by G plus S. Also, what is Ig into G? Ig is Ohm's law, Vg. What is Ig into S? Ig into S is what is Vs. So Vg equal to Vs. Irrespective of their large difference in resistances, their voltages are same. That's the quality of a parallel connection. G by S is equal to Ig by Is. So G by S is equal to Ig by Is. These type of relationships are very important. Okay. Now, this Is, I am writing I minus Ig. So Is can be written as I minus Ig, another relation. Substituting that here, you can get another expression. S is equal to, shunt is equal to Ig G divided by Ig minus G. Ig G by I minus G. So how to get that? Ig into G is equal to, it is not Ig, right? I made some mistake here. Ig G equal to Is, it is Is. Okay, Is. Okay, Ig by S is equal to, so that made a mistake, I make it correct here. G by S is equal to Is divided by, so this is correct. Is is equal to I into G by G plus S, and Ig equal to I into S by G plus S. Now IgG equal to ISS. Okay, so G by S is equal to Is by Ig. Now it's so. Okay. Then again, Is equal to I minus Ig. So that IgG equal to, what is Is? I minus Ig into S. So S is equal to IgG divided by I minus Ig. I minus Ig. IgG by I minus Ig. I minus Ig. Okay, right? So S is equal to IgG by I minus Ig. In most of the cases, I and Ig are not comparable because I may be of few amperes, maybe. For example, large range ammeters, maybe 10 ampere, 50 ampere, 20 ampere range ammeters, 20 ampere, 15 ampere, like that. Ig is normally very small. So I minus Ig, you can neglect Ig. So that IgG by I would be the shunt value. Okay, exactly you will get the shunt like this. Small error you can neglect. So these type of equations are very important. What is the equivalent resistance of the combination of galvanometer and shunt? That is equal to Gs divided by G plus S. And this combination is called ammeter. Let us study what are these parameters. G stands for resistance of galvanometer. Ig stands for full scale deflection current of ammeter. That means current required to produce full scale deflection of galvanometer. If current required to produce unit scale deflection of galvanometer is given, you multiply that with the total number of turns. Total number of divisions. So, current required to produce unit scale deflection of galvanometer is called figure of merit. Figure of merit you multiply with the number of divisions, you will get the value of Ig. Ig stands for total current required for producing full scale deflection. Okay. Now, I stands for the range of ammeter. I stands for range of ammeter. If you have ammeter, milliammeter and microammeter, ammeter has to measure maximum current because its range is large, maximum current. Then ammeter has to flow large current through this so that its resistance should be less. So ammeter has smallest of all the three different types of ammeter, milliammeter, microammeter, which has minimum resistance, ammeter. So which needs a minimum shunt to be connected? Ammeter. So microammeter is required to have a large, comparatively large value of shunt and offers large resistance, right? So that's very important. Now conversion of galvanometer into voltmeter is the last part. For converting, we have to connect a large resistance in series, and this combination will serve as voltmeter. The entering current may be total current, which is Ig. Ig remains same in each. So total voltage across the combination is equal to voltage across galvanometer plus voltage across resistor. Total resistance, equivalent resistance is equal to G plus R. All these factors important. Now V is equal to Vg can be written as Ig into G. Vr can be written as Ig into R. So V equal to Ig into G plus R. This is another important one, from which you can write R is equal to V by Ig. R is equal to V by Ig minus G. This is also important. So conversion of galvanometer into voltmeter. Here V stands for the range of voltmeter. V stands for range of voltmeter. G is the galvanometer resistance. Ig is the full scale deflection current of galvanometer. Okay. Now, let us study the last content of the chapter regarding hydrogen atom. In hydrogen atom, you know that at the center there is a positively charged nucleus. There is only one proton, no neutrons, and electron is revolving around constant radius, circular orbit, non-radiating circular orbit as per Bohr model. Hydrogen atom Bohr model, little bit we can revise Bohr model. The fast moving electrons produces a current. Current equal to charge of electron divided by time period. So current is equal to charge divided by time period is 2 pi r by speed. So EV by 2 pi r is the current. Now magnetic dipole moment is equal to current EV by 2 pi r into area. Area is pi r square for one circular turn. Number of turns is 1. Pi cancel. So moment is equal to EV R by 2, this is also important. This can also be written as EL by 2m, where L is the angular momentum. From Bohr's quantization condition, L is equal to NH by 2 pi. That's very important. L stands for angular momentum, E charge on electron, M mass of electron, mu magnetic dipole moment. Then mu divided by L is a constant, E by 2m. That electron in whichever excited states doesn't matter, ratio of magnetic dipole moment and angular momentum is a constant. Irrespective of whether that electron is in whichever orbits, ratio of magnetic dipole moment and angular momentum is a constant, which is nothing but half the charge to mass ratio of electron, which is E by 2m. It's very popular, important one. Let us write the vector equation for the same. Mu equal to EL by 2m. Last page I have mentioned it. Put vector sign, but with a minus sign. What do you mean by this? Magnetic moment vector and angular momentum vector are in opposite directions. That is the meaning of the negative sign. Okay. Now mu can also be written E by 2m into NH divided by 2 pi. But if n is equal to 1, that is the first Bohr orbit, minimum orbit, first possible orbit, first energy level, ground state, whatever. Mu is minimum. Mu, magnetic dipole moment of hydrogen atom, is minimum when that electron revolving is in the first orbit. That is EH divided by 4 pi m, where m is the mass of electron, H Planck's constant, E charge on electron. Okay, so this is called Bohr magneton. Bohr magneton. And also mu by L is called gyromagnetic ratio. Mu by L is gyromagnetic ratio and mu minimum is called Bohr magneton. So what is Bohr magneton? Minimum magnetic moment of hydrogen atom is called Bohr magneton. Bohr magneton has same units and dimensions as that of magnetic dipole moment. Ampere meter square or Joule per Tesla, both used. Okay, with that I have tried to explain all the topics given in the NCERT quickly. Okay, for a quick revision, as the name says, within the proposed time. Okay, hope that you will be watching this and you will be making use of it. Okay, we will be meeting with the next chapter video soon. Thank you.